So in this afternoon, we're going to have 2 keynotes and 1 parallel session. Before we have the gala dinner in the evening. So I think we should start now. The next presentation will be by one of our keynote speaker, Professor Waragorn Mairiang. Professor Waragorn graduated from Khon Kaen University in bachelor degree in civil engineering and master degree soil engineer in AIT and PhD from Iowa State University. Professor Waragorn joined SEAGC-AGSSEA University and then worked over there until his retirement, and he served in a lot of positions academically. For example, he was the head of the geotechnical division. He the head of the Department of Civil Engineering. He established Geotechnical Engineering Research and Development Center, which is now already 25 years. And professionally, he is a very well-known professional engineer, especially in the field of dam engineering, also in the academic research. He also very well known in landslide engineering, slope stability, and he was one of our former president of Thai Geotechnical Society and chairman of the engineering geotechnical division in EIT. He has so many professional work in the past, many dam that has been designed by him, many dam that has been rehabilitated by him. And this is perhaps one of the topics that he's going to discuss today, is the latest project that is going to start soon. But he did a lot of research and then work on that before we're going to erect the project next month. So everyone, please welcome Professor Waragorn Mairiang.
Thank you very much, Dr. Suthisak, for your kind introductions. On my lectures, I will concentrate on the field monitoring that we go to the serious analysis of field piezometers that can indicate what probably might be the hydraulic fracturings that occur in the dam that we're going to rehabilitate in a short while. Okay. Well, let's go with the introductions. You know, many existing dams had been installed, a lot of instruments. Okay. The main reasons is because of the safety reasons, but only few of the dams will seriously analyze the data for long-term monitoring or long-term behaviors. Oops. Okay. Well, in terms of seepage, is usually monitored by piezometers, observation well, seepage flow meters on the critical sections. And normally, after the five years after the first impounding, many instrument was kind of terminated, did not read at all. Okay, of course, some were out of orders, but many of them just leave it there without continuous reading. Why? They presume that after 5 years reading, the dam's still okay, so it should be okay. Well, the detailed analysis of piezometer response not only reveal the safety precautions, but also reflects the progression of internal erosions or hydraulic fracturings. So if we take it seriously, we can detect the symptom of hydraulic fracturings. So we propose 3 crucial parameters, which is time lags, pore pressure ratio, and trickle level, reservoir trickle level, to quantify the level of hydraulic fracturings that can be occur in the dam. This interpretation not only benefit to the dam owner and the maintenance office, but is also, if combined with the dam monitoring database, it can continuously tell us the condition of internal erosion or hydraulic fracturings. Okay, I will take a short time to review the dam failure statistics. Okay, generally, dam can fail by the instability of the dam itself. Either the downstream slope or upstream slope can fail, can slip, or it can fail by internal erosion, or it can fail by overtopping when you cannot estimate the amount of inflow correctly. But for internal erosion, not only the behavior itself that can damage the dam, but it also well related to slope stability of the dam also. If the pore pressure is getting high, the slope stability, the factor safety of slope stability getting low. And it's at the same time, when part of the dam was failed, then the overtopping can occur also. Okay, this is data from ICO. I think it's quite recently. So most of the dam types belong to earth dam, more than 65%. And the purpose of the dams and mostly for irrigation. It is the same statistic in Thailand also. Most of our dam is for irrigations, okay? And well, let's say for existing dam all over the world, classified by the continents, okay, the ratio of the failed dam can vary according to the location. But in total, the average of the failed dams is around 0.9%, or we can say 1%. Okay, that is quite high. You know, in Thailand, it's not that much actually, fortunately. Okay, and after the dam was complete, the statistics tell that in the first year, or just the first impounding, the dams was failed in a higher percentage, and then it's decreased. Okay, and a long-term data reveal that it will be increased again when the age of the dams is about more than 50 years or 100 years or so. It starts increase again because of deterioration of the material mostly. And it also revealed that, well, before 19th century, so the dam was failed quite a lot. And after that, the technology of dam technology is better, getting better and better, and the number of the dam was failed is reduced. Especially after the World War, I think many military engineers come back from the war, and then they input so many technical, well, for the dams. Okay, and surprisingly, the issue that concerning of the dam failure is geotechnical issue. You see, well, from the past to the present, but it seems to be getting decreasing or lower and lower. And the mode of failure is internal erosion, is the top one, okay? That is something that gives you in mind how important internal erosion of hydraulic fracturings was so important. So now I will lead you to the hydraulic fracturing in dam. Well, in the case study, people said that Teton Dam was a classical failure that we learned a lot from this dam. Okay, the erosion on the right abutment here, about 3/4 of the height starting, and then progress very fast. Then finally, it's completely failed. It fell within 4 hours. Okay, and I think the remnant of the dam still remain for study. I'm not so sure. Professor Nelson can insist. USBR usually keep this dam for the case study. Okay. The panel, independent panel, revealed that is probably due to the arching effects at the narrow core trench of the dam. Because this core trench is so narrow that it creates the arching of the stress that bring the stress within this area become very low. Then if the stress is low, then the pore pressure can exceed the closing stress and can expand the crack or create a new crack. And it is also agree with, maybe some of the first finite elements, I think, is done by University of California at Berkeley. Okay, it's also agree that there will be a zone of low stress over there. And taking a look at the point of seepage, it is revealed that if the water level is there, the area where they probably have a hydraulic fracturing is only a small portion on the green. And it starts to increase when the water level is getting higher and higher. And finally, it's go up to there, okay? That's why it's become the seepage. And also other dams, like this dam, delta dams, which is very narrow paddle clay core, very narrow. You see, very thin. That create the hydraulic fracturing due to the arching of this portion. Okay, so that's why the pore pressure exceeds the minor principal stress in that area. And I myself dealing with this dam designs we call Mae Kuang Dam on the northern part of Thailand, and we find out that the main concrete outlet structure originally designed like that on the left-hand side, and it leaves so many possible of hydraulic fracturing zone. So we recommend that put more concrete and change the shape in order to minimize the possibility of hydraulic fracturing zone. So finally, the shape will be on the right-hand side. And some classic of the failure or damage in our dams in Nakhon Ratchasima is Munbon Dam. Okay, that is internal erosion through the foundations of the dam. And fortunately, we participate in that occasion and also the design of the remedial work of this dam. Okay. And recently in Laos, SEAGC-AGSSEA Nam Noise is also failed. And there is a literature says it might be due to the hydraulic fracturing through the foundation of the dam. But this case is not disclosed yet because it's in the court, still in the court. So we don't know much about the data, okay? And Sherrod also mentioned that if there is any irregular shape of the foundation, even the well-compacted embankment, it can create the low stress zone, okay, or arching zone like that. So in the yellow area, the water can seep through. And on many other dams, like Borden Head dams also, it's happened in the thin clay core, also can spot many of the area that. The data that I myself participate for RID, we investigate about 22 dams. Not all of them are damaged, but we want to see the, possible, what you call the damage in the dam. So it is concluded that the seepage is one of the large percentage. It is the seepage and internal erosion, okay? So what is hydraulic fracturing mean? It means that if there is an existing crack or a new crack that happened from differential settlements or any archings or something like that, the water can seep through. And if you have low stress like sigma 3 is lower than the hydraulic pressure, then the crack is opened up and the seepage progress. Okay? That is a simple equation. But in our case, since the material is the crevasse phyllite, so we presume that there is no tension because it's a crevasse, it separate each other. So first, we want to see any relationship between the crack width with the permeability that increase, okay? Because this should tell us what is the possibility that the seepage should increase with the permeability increase. So we try to set a model. Okay, and using the basics soil mechanics series based on the Moore diagram that analyzes stress, we want to see that if the normal stress here, that normal to the cracks alignment, would be how much, and it would create the closing or opening of the cracks. So we try to use that Moore diagram. Why? Because the orientation of the crack may not be horizontal. It can be vary, it depends on the foliations of the rock, the orientation of the rock structure itself. So let's see, if we take one crack, it should be very small width, not as big as this, but let's say normally the cracks, if existing, it will fill with what we call filler, a piece of rock that flow in first, and if it's not large enough, it will plug in to the crack, okay? And if we build the dam over it, so the stress of the dam will try to close this crack, okay? Then we will use crack with that closing and can be analyzed by finite elements, a simple finite element also. And then after the impounding, the waters in the reservoir start to seep through and start to open the crack again, okay? So these concepts can be modeled by just simple finite elements analysis, though. So we can have an idea how much it will close due to the construction load. Let's say the resource is there, but actually it should be divided into half. This half will close, this half also will close. So I will try to put this part going up so we can see that this is the wall of the crack, this is the wall of the crack, and when the construction loading comes up, the crack's closing, okay? So the crack closing depend on the modulus of the filler. If the filler is strong, the crack closing will be small, okay? So we can analyze that, depend on the modulus, depend on the modulus of the filler, which is not had been studied in detail yet, okay? Then it also depends on the hydraulic pressure that depend on the reservoir elevation also. When the waters impound high elevations, so the pressure that can expand the cracks will be high. Okay, then we think of the rock mass itself doesn't contain only one crack. It may a series of cracks. How much it is, it depends on the quality of the rock itself. So we can assume a simple model that, okay, the crack is here, and there is a certain spacing, and another crack is there also. So with the crack permeability, this is a crack permeability. That means the permeability that the water seeps into the crack is equal to that much, okay? Then if we calculate the whole mass with several cracks, number of cracks, okay? So we can do what we call equivalent permeability of rock mass with the crack. Depend on how many cracks or what is the spacing of the crack. And with that, we can make a relation between the permeability and the crack width and also the crack spacing also. So you see that in this range, the permeability of very, very fine crack is even less than the permeability through the intact rock itself. So I would say this area we call intact rock permeability control. So when the crack is larger than that, so the crack will control the overall permeability. So we can call that rock crack permeability control. Okay. In our case, we also compare to what we test in the field, and it find out that the field permeability range is around that range. So for further analysis, we probably going to use that for further finite elements model. That is agree with the permeability, field permeability test also. Okay, come to the case study, okay? The study dams is the earth-filled dam, 33 meter high and about 400 meters crest length, okay? It was failed once in 1995, okay? The failure is quite classical here. And also the wet area is found on the downstream toe also. Then this is the detail of the slump or slip surface, or you can call scarp, okay? It's about 1 meter. And then the dam owner decided to put the stabilized downstream berm. Of course, it's help for stability, but it doesn't do anything about the internal erosion or the pore pressure in the foundation. So what we're trying to say is this can happen by the complex geology of the dam site itself. This is the dam site, okay? It's essentially is a sedimentary and metamorphic rock. Why is metamorphic? Because the intrusion of igneous rock in both sides intrude later and then squeeze the sedimentary rock into a ripple like that. So from some of our borehole and with the geological that we find out in the field, we can make an initial layer of phyllite like that, okay? So, and the parameter from the field observation was compiled, and then finally we end up with some of the material property for finite elements. And with the finite elements, we can calculate the minor principal stress. And using the what we call Moore diagram, we can take a look at in which part the minor principal stress is lower than the seabed pressure. Okay, when that happens, we can spot the point that on the red dot, and then we can use some simple graphics to map the contour that create the hydraulic fracturing zone like that. Okay. So this zone is depend on the elevation or the level of reservoir impounding also. Let's see, if you have quite low, 146, then there's appear that there's no hydraulic fracturing zone at all. And when we go to 150 meters of mean sea level of the reservoir elevation, it starts to have a spot. Going up again, the hydraulic fracturing zone seems to be clear. And going up more and more, okay? But fortunately, this dam was limited to impound only that much, not over normal high water level. The excess will be released, okay? But even now, that normal high water levels is lower for 2 meters, just for safety sake. So after some final elements modeling, we can set up what would be some index that can tell what possibility of hydraulic fracturing. So we propose something like hydraulic fracturing index here. I will not tell the detail. It consists of, first, it's concerned the geometry, the ratio of the width with the depth of the foliation. Okay. The second term concerning with the reservoir elevations, and the third term, if compare between the modulus of the fill material and the modulus of the rock material that have a foliation like that. Okay. So by that, from the analysis alone, we also can tell the level of possibility of hydraulic fracturing from the analysis, finite element analysis. Why I propose that? Because if you design a new dam, you doesn't have any instrument at all. It doesn't construct. So you have to forecast, is there any possibility that it will be risk for hydraulic fracturing? If so, you have to take care of monitoring later on. Okay? Then come to the existing dam that is already built and monitoring. Well, with a simple instrument that Professor Brand kindly presented this morning, that dealing with the piezometer, he's a student that time, and he brought me a lot of piezometer for testing with my master thesis. Okay, thank for that. So I learned a lot. Okay, so usually the piezometer is the first choice for instrument, and next might be earth pressure cell and seepage flow meter and so on. Okay, maybe most of you are familiar with the instrument, geotechnical instrument already. Okay, for this dam, unfortunately, before the incident, there's no instrument at all. But after the incident and repair work, the dam owner start to install the instrument. So we, after about 20 years without instrument, and from that incident, we get the information about 22 years after that, after we put up the instrument. So the data that we are going to show here is the data for 22 years on the latest period of the dam. Okay? And the number of piezometer is also limited to the dam axis and to the downstream area. Okay? I have to say that the yellow one is the dam embankment itself. The purple one is residual soil. And the lower part of residual soil, that is probably the hydraulic fracturing area or zone. And the brown one here is weather phyllite, and the lower one is much stronger aquatic sheet. And this is a list of instruments. Okay, now how are we going to deal with time lag? You know, when you measure pore pressure in the dams, the response will be late if compared to the reservoir rising. Okay, so the reservoir rising is supposed to be here. Reservoir water level is going up, and if take it at a stable, the pore pressure that measure from the piezometer start to going up later and maybe reach some point below that. Okay. So if compared to the peak from the blue dot to the red dot, this delay is called time lag. Okay? And the time lag comes from two sources. The first is the time of traveling from the reservoir to the area of piezometer that need time, that water to travel. And another is the time that pore pressure around the piezometer tips flow into the sensing instrument in the piezometer itself. Oh, time is up. Okay, I try to finish it up. So it will be traveling times and activated time, okay? And normally, in our case, we can neglect the activated times and only consider only traveling time. Okay, this is the response that we obtained from the field observation. The problem is it's very difficult to compare between the reservoir water level and the observation. So we have to normalize it. Okay, if we take the maximum of each as 100%, so we can compare between reservoir water level and piezometer reading. And with that, we can also compare the time lag on every stage. Okay, even we can take every 10% of the maximum. Okay, that helps a lot because we get more data. Okay, this is the compile of the variation of time lag with time. At the first period here, from 203 to 208, okay, so the time lag even is sometimes is low, but it still have some time lag. About maximum is about over 50 days. But when the period 2 from 2008 to 2013, it's become low, about 10. And for the latest, it doesn't show any time lag at all. That means water can seep through very fast to the piezometer tips. Okay, and if compared to the outsides of the hydraulic fracturing, there's still a time lag, even though it's not very long, but it still has some time lag though. And the time lag also indicates a possibility of washout and plugging alternated. I mean, if the waters come and it wash it out, so the pressure goes very fast, and then if it is plugged, that means it's slowing down. Okay, I will not go into detail, but you see at the area of no hydraulic fracturing zone, the alternate fluctuation of washout and plugging still show. But in the hydraulic fracturing zone, no plugging at all. The second parameter is we call pore pressure ratio. I like to change that to head ratio later on because the pore pressure ratio is maybe same as Skempton pore pressure ratio, something like that. Okay, is the comparison between the reservoir risings and the piezometer head reading. If it is equal, that means pore pressure is close to 1. That means if it's close to 1, that means there's no resistance along the way of seepage. Okay, you will see that on upstream area is 0.9, 0.7 to 0.8, so and so, very high. But below that and outside of hydraulic fracturing area is only 0.3, 0.2, and so on. Okay. And with that, we can easily plot the contour of pore pressure ratio and be able to detect which one is a possibility of the concentrate leak. Okay. And with the help of, the plotting, contour plotting, we also can map the change of the pore pressure ratio. That means in this dam, the pore pressure ratio is start to move to the downstream more and more. That is not very good sign. Okay. Maybe two more. Okay. And the last thing is the trigger level. You see this. Okay, when the reservoir rising at the first state, there's no response from the piezometer. But if it reaches to the trigger level, it starts to move according to the increase of the reservoir water level. So we will use that at the trigger level. That means if the trigger level is lower, that means it's easier to activate the piezometer. Okay. In the possible hydraulic fracturing area, the trigger level always move down or decreasing. That is not a good sign because it's easy to trigger. Okay. But you see on outside of the possible hydraulic fracturing area, the trigger level seems to be constant. Okay. So with the help of two parameter, time lag and pore pressure ratio, we can establish the relationship between the ideal without hydraulic fracturing with the possibility of hydraulic fracturing. That means the time lag will be very, very short, and then the pore pressure ratio will be very high. Okay. Also, with that, we can also classify the range of the risk level also. And we can, like a summary into some guideline. This guideline it cannot apply for the every dam. It should be customized for each dam according to the performance of each dam also. The dam is not the same. The seabed part is not the same. So you have to do that with a particular dam. Okay. Okay, I come to conclusion. I will finish it now. Most of failure cases are from internal erosion. Okay. And hydraulic fracturing is well known among the geotechnical and dam engineers. Okay, like so many dams. Nice. And this study dams is quite a typical earthfield dam. Not very high, not very large, but a small size dam. And finite element will show hydraulic fracturings of the foliation, syncline, anticline, and so on. Okay, and we can conclude as a hydraulic fracturing index. That is good for the designer before we have an instrument. Okay, after we install the instrument and getting the response, especially from the piezometer, we'll use three parameters as time lag, pore pressure ratio, and trigger level to quantify the possibility of the risk of hydraulic fracturing or internal erosion. Then, of course, you know that, trigger level. And the last one is with the combination of the time lag, pore pressure ratio, and trigger level, we can set the risk level for each particular dams. So you can use that to just what is the progression of the internal erosion in the dam. I think it's all. Thank you very much for your attention.
Thank you very much, Professor Varakon. I'm quite amazed with his presentation that he can incorporate his research in the master degree with the time lag together with his experience, 50-year experience in dam engineering, and then came up with this. And also he can incorporate the financial element with the simple equation in order to get the threshold that he just showed. So again, please give a big applause for Professor Varakon. And I would like to present this token of appreciation for him.